Hello and welcome to my CCNP version 8 Enterprise Core Networking lecture review. My name is Arthur Solomon and I'm going to be providing you lecture material for the ENCOR 350-401 exam. So this is going to be several video lectures covering the individual modules or lessons for the CCNP material. So let's jump in and let's see what we can do. Chapter 2 is about spanning tree. So spanning tree is going to be a layer 2 technology to help prevent loops. So in this chapter we're focusing on the fundamentals of spanning tree, and we're going to be looking at rapid spanning tree protocol. So again, the main purpose here is to ensure that if we have multiple switches, let me grab my pen, we have a way to prevent loops from occurring. So if we have 3 switches plugged in, we have a way to softly take down a link so that the loop is prevented. Spanning tree protocol, STP, enables switches to become aware of other switches through advertising and receipt of other bridge protocol data units, BPDU. STP operates by selecting a root bridge and then identifying ports. The different port states will allow us to figure out what port should be going into a disabled state. All of this should be a review from your CCNA, but we will get into the different variations because STP has many variations. We're going to be talking predominantly about RSTP, or Rapid Spanning Tree Protocol. I do have a complete video series on Multiple Spanning Tree Protocol, MST, but that is about 3 hours long just on that protocol alone. Modern day switches can use PVST, RSTP, or MST. So again, we're going to be focusing on RSTP. So a lot of what we're going to do is we're going to relate things back to the original 802.1d, because all of these modes are backwards compatible with that variation. So what that means is learning about our different states. While, again, we're going to focus on 802.1d, this really does apply to almost all of the other ones as well as a foundational knowledge. So, first one is port types. We know we identify a root bridge, and so that means we need to identify the 3 types of ports. For blocking, let me grab my pen. There will be one port that will be selected as a blocking port. All ports leading away from our root bridge will be a designated port. Let's say this is our root bridge. These ports will be our designated ports. They're going to be the ones leading away. The ports that are facing our root bridge will be a root port. And then there are more complex to talk about the ones that are further away, but again, that's later in our lecture. So with this said, we have to talk about some key terms. Root bridge, that's going to be the master switch. After that, we have our protocol unit, our bridge protocol data unit, BPDU, and that's how the switches notify to talk to one another. We need to configure our switches to identify our root bridge, our root, our designated and blocking ports. In reality, by turning on STP, this sets up the configuration for BPDU. We also need to talk about our different forms of BPDU, like the topology change notification or TCN BPDU. This is what's going to be used to communicate changes over layer 2 topologies to other switches. We're also going to talk about our root path costs. That's going to be a core concept when we're talking about our blocking ports. Because in the previous slide, we said designated port, root port, and one blocking port. Well, we have to identify what area will be stopping or what link will be going down. Other key terminology are things like system priority. That will be a 4-bit value setting a priority. The default value is 32,768. This is used to identify what the root bridge will be, because we can set the value, a different value, to manipulate which one will be root bridge if we want to do that. We have a system ID extension, which is the 12-bit value indicated the VLAN information. Again, that's how we get our 4,000 excess VLANs. We have our root bridge identifier. This is the combination of the root bridge system MAC and the system ID and the system priority. You're going to start seeing the system priority, the VLAN, and the MAC address all play a key role in helping to identify the root bridge. We also have a local bridge identifier. This is a combination of the local switch's bridge system MAC, the system ID extension, and the system priority. The local bridge identifier will be attached to all individual switches, not the root bridge identifier, or not the root bridge, because they'll have their root bridge identifier. We will also have an age limit. So this will be the maximum length of time that passes before a bridge port saves its BPDU information. The default is 20 seconds. Then we have our hello timers. Those are the timers that will be advertised through our BPDUs out each of the ports. The default is 2 seconds, but you can manipulate the value change here to whatever is necessary. Then we have our forwarding delay, and that's the amount of time that a port stays in a listening or learning state before it transitions. So again, some of these, like the states, we're going to have to go through again. Those are later slides. And then our timers will also be brought in a little bit later as well. I don't think it's necessary to look at and memorize the timers. This is more of information, but doesn't help. Max age, 20 seconds. Hello timer, 2 seconds. Forwarding delay, up to 15 seconds. These are key pieces of information that might be on your exam. So now let's talk about path costs. That's essentially the cost that will be used to figure out what the best path is. So our link speed, if they're 10 megabits, gigabit, or terabits, we have the way to figure out the cost. The default used to be the short mode cost, which was 100, 19, 4, 2, and then everything above that are 1. In reality, this kind of impacted things as we moved forward. So we actually got the long mode cost, which is a 32-bit value and uses a reference speed of 20 terabits per second. And that way, we have a little bit better understanding of how to address the link speed. So let's see an example. Here we have our switching loop between switch 2, 3, and 1. We can identify which one is our root bridge. It's labeled, so that makes it a little bit easier. This guy is our root bridge as identified. That means the ports leading away from it will be our DP. And that means all ports going back towards it will be our root bridge. And that means in between switch 2 and switch 3, one of them will transition to a designated port, and one of them will transition to a blocking port. And there's a combination of the priority, the system MAC address, and the VLAN identifiers that will be used to identify which one will be the blocking state. If we add in an additional loop, we're going to end up with an additional blocking port. So again, one will transition to a designated port, one will transition to a blocking port. And we're going to get through figuring out which ones they are and why that is. So switch 1 has been identified as the root bridge, and all of the ports have been identified. But how? How did these ports get identified? That's the question. So first of all, the root bridge election, when all the switches get powered on, one has to be identified as the root bridge. At first, they all think they're the root bridge, and then they have to run through to figure out, well, which one is the actual root bridge. So there's an election. So basically, as the switch initializes, it will assume that it's the root bridge, and it will use the local identifier as the root bridge identifier. It will then listen to the neighbor's BPDUs, and then it will do the following. If the neighbor's configuration BPDU is inferior to its own, then the switch will ignore it. If the neighbor configuration BPDU is preferred to its own, then the switch will update its local table to replace the root bridge identifier. And this will propagate. This will happen to all the switches. They have to listen to one another to identify which one is actually going to be the preferred method. This process will continue till all switches in the topology have identified which switch is the root bridge. So what do we mean by preferred? STP prefers the lower priority. And if all of them have the default priority, then it will go to the lowest MAC address. So again, there is a process. So once we identify which is the root bridge, then we have to figure out the path costs. We already know that the root bridge, all of their ports will be designated ports. So these ports will automatically be recognized. But what ends up happening is we need to start figuring out, well, what are the costs? So looking at this cost, we're looking at path costs. And then going from here to here, we have an additional path cost. Looks like they are gig. So actually, I'm going to go back a few slides. We are using the shortest mode path cost for. So this hop is no cost, this hop is no costs. So this cost will be 4. Now in reality, we could definitely say that every link is going to be whatever the appropriate cost is. But we can start figuring out what the costs are. To identify the different paths and the cost that will be. Let's say these two links don't exist. To go this path, that's 4. To go this path, so if switch 4 had to get to our root bridge, it would be 4 plus 4 plus 4. SW4 to go to SW1 would be a path of a cost of 12, assuming these links are down. That is how the costs are calculated. The route path cost is always going to be 0. So this one, in your CCNA, it always says to calculate them. So if we're just doing these, this would be plus 0, this would be plus 4, that would be plus 4. Updated cost would be 8 if we are not using the route path costs. And again, those are things that you have to be aware of. So locating the ports, that's going to be the next question. Once we've identified the route bridge and we have an understanding of the costs, then we can start figuring out what are the route ports. The route port is selected using these next 5 steps. The steps are: identify the interfaces associated with the lowest path costs. That's going to be the more preferred costs. The interface associated with the lowest system priority of the advertising switch is the next preferred. Third, interface associated with the lowest system MAC address of the advertising switch is then preferred. When multiple links are associated with the same switch, the lowest port priority from the advertising switch will be preferred. After that, when multiple links are associated with the same switch, the lower port number. This will use the lowest port priority. The last one will use the lowest port number, and that would be preferred. Again, there is a structure here. It's not just willy-nilly. So, lowest system priority, lowest costs, lowest system priority, lowest MAC, lowest port priority, lowest port number. That's the overall structure. So talking about it doesn't really help as much. We need to be able to see it. So let's hop in, and if we do a show spanning tree route on each of our switches, here we have switch 5, 4, 2, and 3, don't have switch 1, we can start to identify the route ID. And that's one that is continuously listed on all of them. And it should also tell you the route costs. And it should also tell you the port. Which ports are route ports. It will also give you the timer details. So, now that we have an understanding of viewing the route port, then we have the ability to start trying to identify the blocking designated switch port. So the blocking port. So to do that, we need to first identify what are the route ports, what are the non-route ports, what are the non-route switches. We need to figure out what switches are what ports are what. That way we can figure out where the potential blocking state should be implemented. That way we could prevent the forwarding loop. So we do that by checking the interface. That will be a designated port. It must not be considered an RP. That may not be a route port. So that means they cannot be part of the pathway leading towards the route bridge. The switch with the lowest path cost to the route bridge forward, and the one with the higher path cost blocks. If there's a tie, they go on to the next step. Meaning, if there are two ports that are looking, one might be a designated port, one might be a blocking port. We have to look at the costs. What we do is we figure out the appropriate cost. The first step is the system priority of the local switch will be compared to the system priority of the remote switch. We compare both switches. The local port is moved to a blocking state if the remote system priority is lower than that of the local switch. If they tie, they go on to the system MAC address of the local switch. So, again, what exactly does that mean? Let me grab my pen. Designated port. So we're assuming this is the root bridge. These two are two unknown ports. So one will be switch A, one will be switch B. So the system priority of switch A will be compared to the system priority of switch B. If they're both the same system priority, the default, then we move on to the system MAC address of switch A, and then we compare it to the system MAC of the remote switch. We compare the MAC addresses. Whatever the MAC address is, the lower one. So if this one has a lower MAC address, then this side will go to blocking. And this one will go to a designated port. If switch B has a lower MAC address, that'll be a designated port, and this one will go to blocking. So there actually is a structure for our port designation. They're not just random. There's actually an election process held for each individual step. So after we do that, we have to verify the information. So here we have our spanning tree on VLAN 1. So we can see a P2P or we could see a P2P edge. So these port types are expected on our switches. So we should have an area for our root ID, and you should see that they show the priority. They show the MAC address. They will also identify if it's the root bridge or not. After that, we can see again priority, the system ID extension. Again, that's the VLAN. We could see the timers, and then we could see the types. So this is a designated port. This is forwarding. These are the costs. And then these are the types. The P2P, basically this is the type of port with another network device. So a PC or another switch or something like that. A P2P edge, this port type specifies port fasts, or it's connected to a end device. I know that this one also said PC, but in reality, this guy should be networking devices. So if the PC is running like a router, things like that. We can also look at more detail with a show spanning tree VLAN 1. We can look at the costs. We can look at the ports. We could see the role if it's a root port or a designated port. We can see that none of these are port fast enabled, so none of them are edge devices. None of them are computers. So all of these are connecting to other switches. Here we have a show spanning tree interface looking at a specific interface. We can see the port. We can see the VLAN it's attached to. We can see the port path costs. We can look at details on a trunk or on an edge link. We have the ability. The big thing here is understanding how much data to be reviewing and kind of what all that data means. So you'll notice this is omitted. There's a large chunk of data that's there. So with topology changes will be done through a BPDU, and they will always flow from the root bridge to the edge switches, unless there's a massive change in the topology. If the topology does change, we should get a TCN BPDU, and that'll be heading towards the root bridge. So if there is no topology change, root bridge down. If there is a topology change, it will be that change going back to the root bridge. So if an upstream switch receives a TCN, it will send out an acknowledgement and forward it to the root bridge, and it will forward it out the root port to the root bridge, and then it will take it all the way. We keep doing a 3-device network, but what happens when we have lots of switches, lots of interconnects? That's why STP is there, so we can identify the loops and prevent them. And if there is a massive change, then we can get our topology change notifications so that we could recalculate the appropriate paths. When the receipt of a TCN is received, the root bridge will create a new configuration BPDU. The topology change flag is set, and then it's flooded to all other switches. It's going to change the flow of our layer 2 switching data. When the switch receives this, they set their MAC address timer to the default 15 seconds. Then they flush their MAC address table if it is not heard from a device after that 15 seconds. TCNs are generated on a VLAN basis, so the impact of a TCN directly correlates to the number of hosts on that VLAN. This structure is happening anytime there is a modification. So we can look at a show spanning tree VLAN, and we can look at the details. We would have to identify the VLAN number, and issue a detail. And then we can look at the number of topology changes that have occurred and last time the change occurred. And we can also get on the interface. So there is a much broader structure when we are talking spanning tree. It is not simple turn it on and forget. That's the default, and it will work. However, we can do a lot to control the flow of communication. So all of these changes basically allow for the convergence of our switches. Convergence is basically sharing the data. So when a switch will lose power or reboot, when a cable is removed from a port, so we have layer 1 saying, hey, port state's down. We can notify other processes, such as STP, in such a way. So STP considers such an event a direct link failure, and it can react in an appropriate manner. The link between the two switches, if it fails, the link is already blocking, there is no impact. So if we are looking at if this link is down and it's in a blocking state, then nothing happens. So there's no impact to the traffic between the two switches as they're both transmitting out those ports. So we don't have to really worry. If, however, the link between switch 1 and 3 fails, and this was the blocking port, then we have to reshift the traffic. there should be a TCN, and then the traffic from switch 1 and 2 will have to accommodate. So instead of traffic going that way, traffic is going to have to go that way. So all of this will then transition the way the ports are. So if this link is down, one of these will be transitioned to a blocking state. If the link between switch 1 and 2 fails, then the network traffic will be reversed, so it'll go the other way. So if that link goes down, then traffic will have to flow that way, and that will be a blocking state. So there is a structure to make sure that we can ensure that the flow of data at layer 2 is always going. So let's look at an example. So here we have our devices. Phase 1. A link goes down. Switch 1 will detect a link failure on its gig 103 interface. So let's draw this out. Link down. This interface says, ooh, something's weird going on. TCN. TCN notifies the root bridge. Root bridge knows normally data from switch 1 will go to switch 3. So normally switch 1 would generate a TCN flag out its root ports, but it's the root bridge, so it does not do that. Switch 1 will then advertise a TCN if it were not the root bridge. SW3 will remove its best PDU received off that port, and then it will do a downstate. Switch 3 would attempt to send a TCN towards the root bridge, switching to notify if the topology has changed. However, this port is down. So what happens? Phase 3, the switch 1 will advertise a configuration change with the topology change because it detected the change. This BPDU is received and related to all switches. So this port is now down, this port is now down. So we're going to go ahead and send it to switch 2. Switch 2 will get it and it will forward to all other switches. It will receive and relay the change. So with that, switch 2 and switch 3 will receive the configuration BPDU with the topology change. These switches will then reduce the MAC address age timer to forward delay timer to flush out older MAC addresses. In this phase, switch 2 does not know what changed in the topology. Next, switch 3 must wait until it hears from the root bridge again, or the max age 20-second timer will have to expire before it can reset the port state, because right now this is a root port still. So the switch will have to receive it and wait. Once the timer expires, it can reset the port state and start to listen. So I know this is a blocked port. It will start listening on that port because the blocking state will go away and it will transition back to a listening state so it can figure out what to do. So let's run through this process again. But what happens if the link between switch 1 and switch 2 fails? So again, same process. Switch 1 should identify that a link failure has occurred on its interface. Switch 2 will detect a link failure on its gig interface. But notice these are slightly different now. So what that means is, let me grab my pen. This was a root port, yes, but switch 2 will detect a link failure on its interface. on its gig 103 interface. Normally, switch 1 would generate a flag change. So again, I think this is gig 0102 will detect it. It will figure it out. Link failure. These two will figure out that they need to. The fact that the link failure here is down, it can't, because again, while it is an root port, the link failure is down. This side is a designated port, so it cannot move out. So switch 2 will remove its best PDU from its path because it's now in a down state. This is now down. Switch 2 will attempt to send a TC in towards the switch to notify the change. Phase 3, switch 2 will advertise a configuration change where its root bridge the switch 3 port is in a blocking state, and so it cannot relay to switch 3 as its port is still in a blocking state. So switch 2 will assume that it's now the root bridge. Phase 4, the switch 3 will receive the configuration from switch 1. And from there, it will recognize, oh, there's been a failure. The blocking state should be removed. Switch 3 will reduce the MAC address age timer to the forwarding delay timer to flush out all the MAC addresses. Switch 3 will receive inferior BPUs from switch W2 and discard them as it's still receiving things from the actual root bridge, not the switch 2 that thinks it's the root bridge. The max age timer on switch 3 will expire. Now the gig 01 port on switch 3 will transition. That's the actual transition. It can now forward data. Phase 6, switch 3 will receive the configuration BPDU on the switch via SW3 and recognize it as a superior. So switch 2 will now figure out, oh, I'm not really the root bridge, and then will process it. All of this time takes about 52 seconds for this process to re-engage the downed link. And that's the ideal time. It is a process for STP, but it's one of those that, well, when we have multiple switches, we actually need to be mindful of. Those are all direct link failures. What happens if there is an indirect failure? So STP will communicate between the switches if there is an impaired or filtered link. While the network link remains up, the situation is known as an indirect link failure, and the timers are required to detect and remediate the topology. So for example, between switch 1 and switch 3, if the data is impaired, not that the link is down, but something has occurred and the link is impaired, what do we do? An event occurs, switch 3 will stop receiving the configuration BPDUs on its root port. It will keep a cached entry on gig 101. The configuration BPDU from switch 1 that are being transmitted via switch 2 will be discarded as it's on the gig 102 port, and that's a blocking port. There has to be an age timer, so once the age timer expires on switch 3, it will flush the cached entries of the root port, and then switch 3 will transition the blocking port to a listening port so that it can then move forward. So after that, we have to go to phase 3, which switch 2 will continue to advertise the configuration PPDUs from switch 1 towards switch 3, and then the phase 4, basically SW3 will receive the switch 1 configuration PPDU via switch W2 on its 102 interface, which was formerly blocked but now is in a listening state, so that they can identify the impaired or corrupted link and then adjust that to a blocking state. Again, reconvergence is about 52 seconds. So again, there is a process to make sure that whether the link is fully down or partially down, that data can still flow correctly. Alright, next major section is understanding RSTP, or Rapid Spanning Tree Protocol. While 802.1d has been one topology tree and it is a little slower on the convergence, which can be problematic, 802.1w does reduce the number of port states to a faster and more efficient processing ability. So instead of having all the port states and all of that things, RSTP is a little faster, and that's what a modern day switch uses. Alright, so let's examine those additional port states. So we went from 5 port states down to 3 port states. Port states being discarded, learning, and forwarding. Instead of having a bunch of additional timers and waiting, we have just these 3. So discarding is basically the switch port is enabled, but the port is not forwarding any traffic. That way, a loop is not created. In the learning stage, the switch port will modify the MAC address table. The switch still does not forward any of the traffic, it's just receiving. And after that, we move to a forwarding state, and that's where the switch port will forward all network traffic and updates the MAC address as normal. Forwarding is the normal operation. When a switch first comes on, it loads discarding, holds down timer, and then switches to a learning state, holds down X amount of timer, and then transitions to a forwarding state. So again, 802.1d has one topology tree, which can be problematic. Larger environments need to be more flexible. With VLANs, we need something that can handle multiple things. So we had the per VLAN spanning tree, or PVST, or PVST plus. So both of these transition to the Rapid Spanning Tree Protocol, which will reduce the number of port states from 5 down to 3. So we're going to be focusing on RSTP. Again, we still have the predominant root port, designated port, but now we have an alternate and a backup port. So root port, again, we know that those are ports going towards the root bridge, more of an upstream, where designated ports are more the downstream. An alternate port is a network port that provides alternate connectivities towards the root port through a different switch. So normally when we identify our ports, we're focusing on RP and DP. But because this can also be done per VLAN, we're going to have to look at this per VLAN link and not necessarily for just the layer 2 fabric by itself. A backup port is a network port that provides a link redundancy towards the current root switch. A backup port will exist only when multiple links are connected between the same switch. Alright, so moving past that, we have our edge ports, root ports, and point-to-point ports. So an edge port is just that. It's a port at the edge of the network where end devices connect. A root port, that's the port that has the best path cost towards the root bridge. And a point-to-point port are basically any port that connects to another network device with full duplex. Again, that's normally point-to-point is going to be pointing towards another switch. So building this RSTP topology, how does all of this work together? Basically, you configure RSTP, turn it on. They will establish a bidirectional handshake across the shared link to identify the root bridges. To do that, the process is as follows. The first 2 switches connect to each other. They verify that they are connected with a point-to-point link by checking the full duplex status. Once that has occurred, they will establish the handshake with each other via an advertised proposal. that will be the configuration BPDU, that their interface should be the designated port for that port, because they'll both identify as the root bridge at that point. They can be only one DP per segment, so each switch will identify whether it's the superior or inferior switch based off of the priority, based off of the extended VLAN ID, based off of the lowest MAC address. Using the same logic as the 802.1d protocol for STP, that will use the system identifier. Again, lowest priority, lowest MAC. After that, the inferior switch, in this example, switch 2 will recognize that it's the inferior and will mark its local port as the root port. At the same time, it will move all non-edge ports to a discarding state. At this point in time, the switch has stopped all local switching for non-edge port devices. Again, this is temporarily just for a few seconds. The edge devices will still be able to do local communication, but it is negotiating with the other non-edge ports so that it can figure out who's going to be what port state and move forward. The inferior switch will send an agreement configuration BPDU to the root bridge, which signifies to the root bridge that synchronization has occurred. The inferior switch will move its RP to a forwarding state after the appropriate timer has been happening. Then the superior switch will move its DP to a forwarding state too. The inferior switch will repeat the process for any downstream switches it's connected to, and so forth. Alright, so that's the end of this chapter. We've looked at our different types of ports, STP, and all of the main key topics. Key terms are going to be things like BPDU, configuration BPDU, hello timers, the port types, designated port, root port, blocking port, the bridge identifiers, both local and root bridge identifiers, the topology, change notification BPDU, the TCN BPDU, so forth. We also looked at several command references, spanning tree VLAN, show spanning tree root, show spanning tree VLAN, show spanning tree VLAN, specific VLAN detail, and so forth. And that is the end of this chapter. Thank you. Alright, so that wraps up this module. If you have any questions or concerns, definitely feel free to reach out. Post a comment, ask a question. Remember, as we're going through this material, it's common to be able to take some time, gather your thoughts, ask some questions so that we can really work on retention and getting you more familiar with the material. Thank you.